Hi, my name is WebAI 360. Please subscribe my channel for technology news and AI updates. In this video we'll discuss about training an AI model using a comprehensive step-by-step guide. In the rapidly evolving field of artificial intelligence, leveraging the power of existing models to train new ones has become a popular strategy. Whether you're interested in knowledge distillation, transfer learning, or simply using a robust pre-trained model to guide the training of a smaller, more specialized model, this approach can significantly reduce training time and improve performance. In this article, we'll break down the process into clear, actionable steps, complete with detailed explanations and practical tips. Understanding the concept, model-to-model training. Before diving into the steps, it's important to grasp the underlying concepts that make training one AI model using another both possible and effective. What is knowledge distillation? Knowledge distillation is a technique where a teacher model, typically a large, well-trained network, transfers its learned knowledge to a student model, a smaller or less complex network. The idea is to have the student mimic the teacher's behavior by learning from its outputs rather than starting from scratch. This is particularly useful when deploying models in resource-constrained environments, such as mobile devices. What is transfer learning? Transfer learning involves taking a model trained on one task and repurposing it for another, often related, task. By reusing features learned from a large dataset, you can reduce the amount of data and computational resources required to train a new model. Both methods share the common goal of leveraging pre-existing knowledge to enhance the performance of a new model. In this guide, we'll focus primarily on the process of knowledge distillation, though many of the principles apply to transfer learning as well. Step 1. Define your problem and choose the right models. Every successful AI project starts with a clear understanding of the problem you're trying to solve. Once you have defined the task, you can decide on the teacher and student models. Define your problem. Identify the task. Is your goal image classification, natural language processing, or something else? Clearly defining the task will help in choosing an appropriate teacher model. Determine constraints. Consider factors like computational resources, latency requirements, and memory limitations that might affect your choice of models. Choose the teacher model. Pre-trained models. Look for well-established, pre-trained models in your domain, e.g., ResNet or Inception for image tasks, BERT or GPT for language tasks. These models have been trained on large datasets and capture a wide range of features. Performance and complexity. A high-performing teacher model can offer more accurate, soft targets for the student, even though it might be too large for deployment. Choose the student model. Size and speed. The student model should be more compact and efficient while still being capable of learning from the teacher. Flexibility. Ensure that the architecture of the student model is compatible with the distillation process. Some architectures are more amenable to knowledge transfer than others. Step 2. Data collection and preparation. Data is the backbone of any AI project. Proper data preparation ensures that both the teacher and student models can learn effectively. Data collection. Gather a large dataset. For the teacher model, you may require a large dataset that covers the range of features necessary for your task. Domain-specific data. Ensure that the dataset is relevant to your specific use case. This might involve collecting domain-specific images, texts, or other data types. Data preprocessing. Cleaning and labeling. Remove noise and errors from the data. Ensure that labels are accurate to maximize learning potential. Normalization and augmentation. Normalize the data to a consistent scale and consider data augmentation techniques to improve model robustness. Splitting the data. Divide your dataset into training, validation, and test sets. This ensures that you can measure the performance of both the teacher and student models reliably. Step 3. Training the teacher model. The teacher model serves as the benchmark from which the student model learns. Training or fine-tuning this model properly is crucial. Training strategies. Pre-training versus fine-tuning. If a pre-trained model exists, you may only need to fine-tune it on your specific dataset. Fine-tuning involves updating the model weights with your data while retaining much of the learned features. Hyperparameter tuning. Experiment with learning rates, batch sizes, and optimizers to achieve optimal performance. Regular evaluation. Use a validation set to monitor performance throughout training. This helps in early detection of overfitting or other issues. Save the model and extract knowledge. Model checkpoints. Save periodic checkpoints of the teacher model during training. These checkpoints can be useful for later comparison and for initiating the distillation process. Extract soft targets. For knowledge distillation, the teacher's output probabilities, soft targets, are more informative than hard labels. These probabilities contain nuanced information about class similarities and decision boundaries. Step 4. The knowledge distillation process. Once the teacher model is performing well, it's time to begin the knowledge transfer to the student model. Teacher's role in training the student. Generate soft targets. Run the teacher model on the training dataset to generate soft targets. These probabilities will guide the student model. Temperature scaling. Apply temperature scaling to soften the teacher model's outputs further. A higher temperature produces a smoother probability distribution, which can help the student model learn better. Setting up the distillation framework. Loss functions. Combine the traditional loss, such as cross-entropy with the true labels, with a distillation loss that measures the difference between the student's predictions and the teacher's soft targets. Balancing the losses. Use a weighting factor to balance the contribution of the traditional loss and the distillation loss. Experimenting with different weights may be necessary to find the optimal balance. Step 5. Training the student model. Now, the focus shifts to the student model, which is trained using the distilled knowledge from the teacher. Design the student model architecture. Simplicity and efficiency. The student model should be less complex than the teacher, designed to be more efficient while still capturing the essential features of the task. Compatibility. Ensure that the architecture supports the integration of distillation loss during training. Training process. Combine losses. Implement a composite loss function that includes both the traditional task loss and the distillation loss. Iterative training. Train the student model iteratively, gradually increasing the weight of the distillation component as it starts to mimic the teacher. Regular evaluation. Monitor the student model's performance using the same metrics as the teacher. Validate on a separate dataset to check for overfitting or performance degradation. Hyperparameter tuning for the student. Learning rate and batch size. Optimize these parameters specifically for the student model. Distillation temperature and weighting. Experiment with the temperature scaling factor and the weighting of the distillation loss to ensure effective knowledge transfer. Step 6. Evaluation, iteration, and deployment. After training, it's important to rigorously evaluate the student model and iterate based on the results. Evaluate model performance. Metrics and benchmarks. Compare the performance of the student model against the teacher model using accuracy, precision, recall, F1 score, or other relevant metrics. Real-world testing. If possible, test the model in real-world scenarios to assess its practical performance and robustness. Iterative improvements. Fine-tuning. Based on evaluation results, fine-tune the student model further. Adjust hyperparameters or modify the loss weighting as needed. Error analysis. Analyze cases where the student model underperforms compared to the teacher. This can provide insights into areas for improvement. Deployment considerations. Efficiency and latency. Ensure that the student model meets the required efficiency standards for deployment, especially if it is intended for real-time applications. Monitoring. Post-deployment. Continuously monitor the model's performance and update it periodically with new data or improved training techniques. Conclusion. Training an AI model using another model is a powerful technique that leverages pre-existing knowledge to build more efficient and effective systems. By carefully selecting your teacher and student models, preparing quality data, and employing techniques like knowledge distillation, you can significantly improve the performance of a compact model while reducing training time and computational requirements. This step-by-step guide has outlined the entire process, from defining the problem and preparing the data to training the teacher and student models, and finally, evaluating and deploying the solution. As AI continues to evolve, mastering these techniques will be essential for developing innovative, scalable, and high-performance models that meet the demands of various applications. Embrace these methods in your next project, and unlock the potential of training smarter, more efficient AI systems using the strengths of established models. DeepSeek is an innovative AI model that was developed by leveraging the advanced capabilities of the ChatGPT model as a guiding mentor. In its training process, DeepSeek adopted a teacher-student framework, where ChatGPT's well-honed language understanding and nuanced responses served as a benchmark for learning. This approach allowed DeepSeek to absorb intricate language patterns and contextual subtleties, effectively narrowing the performance gap between complex deep learning architectures and more streamlined, application-specific models. During training, ChatGPT was used to generate high-quality, context-rich responses that acted as soft targets for DeepSeek. These soft targets provided a detailed, probabilistic insight into language usage, enabling DeepSeek to learn not only from explicit labels but also from the relative importance and interplay of various linguistic features. Techniques such as knowledge distillation were employed, where DeepSeek's predictions were iteratively compared and aligned with ChatGPT's outputs. This method ensured that DeepSeek captured the depth of ChatGPT's reasoning, facilitating a more refined and robust learning process. The outcome of this synergistic training strategy was a model that combines efficiency with a deep understanding of language. By inheriting the sophisticated insights of ChatGPT, DeepSeek demonstrated enhanced performance in language processing tasks, showcasing improved accuracy and contextual awareness. This innovative training paradigm not only underscored the effectiveness of teacher-student models but also highlighted the potential of using established AI systems to accelerate the development of new, domain-specific models in the evolving landscape of artificial intelligence.